Okay, hello everyone. Welcome to session 2 of day 1. My name is Alicia Sarah and I will be the moderator for the session. Okay, let me invite our speakers for today.
Hi.
Hello, Mr. Ali Akbar.
Hi.
Okay, let me introduce our speakers today. Mr. Ali Akbar Septiandri is from Universitas Al Azhar Indonesia as an
Yeah.
adjunct lecturer. Mr. Ali is learning and teaching data science, machine learning, and artificial intelligence. Mr. Ali is also a host of Tentang Data podcast. Wow,
Yes.
interesting. Okay, in this session, Mr. Ali will deliver a talk about introduction of probabilistic programming with PyMC3. This
Yes.
talk will introduce a probabilistic programming framework to do a Bayesian inference, right? Sounds
Yes.
good, yeah? Okay, so I remind for all the participants, you can keep these questions coming up on Hopin platform. We'll discuss it in a Q&A session, okay? Okay, without any further ado, let's have a huge virtual applause for Mr. Ali Akbar Septiandri. Stage is yours.
Right. Okay. Thanks, Sarah. Today I'd like to talk about introduction to probabilistic programming with PyMC3. This will be a talk that needs a little bit of probability theory, so I expect you have to have it first. Um, so the talk is about big data versus small data. Actually, some fields of study don't have the luxury of big data. For example, in healthcare, you cannot just get a person sick on purpose, or in oil mining, you cannot just drill wherever you want. It's just not possible. So some of the cases you don't have the luxury to get big data, so you have to deal with small data. um, and also, when you're talking about big data, as Andrew Gelman said, once n is large enough, you can start subdividing the data to learn more. So n is never enough, because if it were enough, you already be on the next problem for which you need more data. So we in data analysis, exploratory data analysis, we always do subgroup analysis, and for that we need more data. But if it is big enough, then we can do subgroup analysis, and so on and so forth. So you kind of always deal with small data at the end of the day, and for that you may find Bayesian inference useful. So this is one field of the probability theory, or probability and statistics in general, uh, uh, coined by the Reverend Thomas Bayes from the University of Edinburgh. So yeah, for this case, or for this study, Bayesian inference, you can actually learn from these two references, two great references. The first one is Bayesian Methods for Hackers book by Cameron Davidson Pilon. It's a very good book. It has a hacker first mindset. So yeah, with code from PyMC3, you can learn a lot from this book. And actually, this talk is heavily based on that book as well. And the other book is Statistical Thinking from Richard McElrath from the Max Planck Institute of Evolutionary Anthropology, if I'm not mistaken. He also includes some snippets of the code to do Bayesian inference, but in R. But some of the nice guys out there have already ported the code to PyMC3 as well. So in real cases, where do we find PyMC3? Actually, it goes all the way to SpaceX. So yeah, in a way, to the outer space. This Ravin Kumar is he was engineer. He was an engineer at SpaceX, and he used PyMC3 in his job. So the interesting thing is that in SpaceX, you don't really have that many rocket ships. You don't just conjure up rocket ships out of nowhere. So you have to deal with only a handful of rocket ships. If I recall correctly, he said that there are only 16 back then rocket ships. So yeah, it's you cannot right deal with big data in that case. And Bayesian statistics is about updating your prior belief after observing some data. John Maynard Keynes said, "When the facts change, I change my mind." So, what can we do with this? How can we incorporate new data, so the latest version of the data, to update our belief in something? Uh, an Asian worldview interprets probability as measure of believability in an event. So instead of using the long run frequency of something in Bayesian, we it's just that we say we believe that something will happen with this probability, this and this probability, and yeah, it's that simple in the interpretability. So yeah, as I said before, this is based on a base rule, so probability theory, specifically base rule, where we have the prior, the likelihood, and the posterior, and also the normalizing constant. But in this case, when we are dealing with Bayesian inference, the normalizing constant will be uh, calculated, or we will sample from the posterior using this library. So we don't really have to deal with finding the normalizing constant, which is cumbersome in most of the cases. And in the frequentist side, they assume probability is the long run frequency of events. So in the mathematical formula would look something like this. So probability of an event is the number of events divided by n, or the number of data when n goes to infinity. So to give you a more concrete example, if you see these two images, where would you go to have a coffee? The left one or the right one? Please ignore the bajai in the picture. I know most of you won't go to the right because yeah, it's a coffee shop. Why would you have it in a bajai? So, like most people out there, you would probably pick the left one, right? Albeit the left one having only 4.5 average score, or stars. It is you believe more about the um, credential, or the yeah, you would go to the left one because most more people uh, review there, um, compared to the right one. Yeah, so more than 1,000 reviewers. um, so yeah, why is that? Why do we believe more in the left coffee shop instead of the right coffee shop? um, so that's the problem of true value versus observed value. So as we acquire more and more instances of evidence, our prior belief is washed out by the new evidence. um, and then when n goes to infinity, the two views actually align. Like the Bayesian and the frequentist views, those will be aligned. Um, but by introducing prior uncertainty about events, we are already admitting that any guess we make is potentially very wrong. So, what we are trying to do here is to find less wrong answers. Yeah, and so after, uh, yeah, so George Box said that all models are wrong, but some are useful, and in this case, we want to find less wrong answers based on what we have observed. So, are the frequentist methods incorrect then? No, they are not incorrect. They are powerful and fast. Most of you who deal with machine learning usually use the frequentist side of the yeah, method. And the problem is frequentist method is not flexible. You can only say that it is statistically significant or not, and you focus on that, and it's not straightforward. It's not easy to interpret. So most of your interpretation on the model would likely to be incorrect. So yeah, but on the other side, Bayesian methods are straightforward. You can what you and intuitive in a way. So with all good probability theory and yeah statistical theories, there's always this mandatory coin flip example. So we'll start with this. So the case is like this: we'll toss a coin n times. What is the probability of seeing a head? In this case, frequencies coin flip will model this as a random variable x that follows a Bernoulli distribution with parameter theta. So after several coin tosses, you'll see several heads, and you'll update. You'll have the maximum likelihood estimation of the theta. And what you can say is that whether these value, the theta values, are statistically significant or not. But you don't really make much of it in this case. And you can also see that even when you have different values of theta, like the same values of theta, like for example in the 5 coin tosses and the 15 coin tosses, uh, you cannot tell the difference. You only have the theta value, but um, it's likely to be the same from your standpoint. But in Bayesian theory, Bayesian statistics, when you're doing Bayesian coin flip, you update your belief in the value of theta when you're observing more data. So, for example, at the top left figure, you'll see that the when zero observed tosses, and you get zero heads, the probability of the probability of theta goes from 0 to 1, and you don't know for sure. Equiprobable. But when you have observed one tosses and one heads, the probability of theta being zero will uh, be zero as well, because there's no way you'll get theta of zero when you have already observed that the coin flip will be had in first time. So yeah, it's a bit harder since we are also modeling the theta now with beta distribution with the parameters a and b. And a beta distribution, it looks something like this. The support is between 0 and 1, and it's a numerical value. So it's in a way it's a probability of a probability. Um, and the formula for beta distribution is in a way a lot more complicated than your usual distribution like Bernoulli or binomial. But in theory, it is and it has a nice property that can relate itself to the beta and the binomial distribution. The Bernoulli and the binomial distribution. So another more concrete case and a more relatable one to you, A/B testing. So in A/B testing, you would like to prepare the sample size calculator. For those of you who are familiar with A/B testing, maybe you're familiar with these A/B test tools or something similar, where you have to define the baseline conversion rate, minimum detectable effect, and the statistical power, significance level, and then you'll get the sample size. But you don't really know. I suspect that you don't really know what you're doing in this case. So that's of no use. You'll just follow what has been done previously by other people. Um, in the Bayesian way, it's not that easy either. So you want to define whether a conversion rate of the B group will be larger than the A group. But in this case, you will start with something like this. Like I mentioned earlier, you'll need the beta distribution in this case, and you'll have to derive it. Blah 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 blah, and most of you will leave this talk by this time, and you'll get something like this. Eventually you have to deal with the beta distribution of beta function and the summation, and yeah, all this formula. uh yeah, hopefully this doesn't repel you. But anyway, so let's get a more concrete example, and how PyMC3 or probabilistic programming can help you with this, to avoid this integrals. I know most of you hate integrals. So yeah, for a simple example and a more concrete one, we'll start with this. Group A has 1027 impressions and 313 of them converted, and while Group B has 1032 impressions and 308 of them converted. And the problem is always which one is better, Group A or Group B. So if you already have basic probability theory, basic probability understanding, you'll get to something like this. Yeah, start from something we know. So the first two, the uniform distribution, you basically say that you don't know anything about the conversion rate. So that those are the priors of this model, and then you model the outcome of the conversion as y, so ya and yb. Those values or those random variables follow a binomial distribution with their respected um, parameters, yeah, 1027, and PA 1062, and PB. And what we want to know is really the posterior in this case. So what's the probability of PB greater than PA given YA is 313 and YB is 308? So looking at this, this should be much simpler to you. And PyMC3 or probabilistic programming library can help you to model this easily. So in the code, it would look something like this. So pretty similar to what we have defined before. So in this way, we can use, yeah, something simple like the uniform distribution instead of using the Bayer distribution. Then in the last line, you'll see the trace or pm.sample that would do the job, uh, yeah, easily. So you'll get something like this, some nice plots. You'll see this is known as the trace plot, the PAPB, and the difference. And you'll see that I kind of reformulate the question here. Previously, we want to know whether the probability of PB be greater than PA. But in this case, we'll see diff here. A diff means that PB minus PA is greater than zero. So we want to know the probability of PB minus PA be greater than zero. Yeah. So after the formulation and doing the sampling using PyMC3, or in this case, the nut sampler, you'll get this. You'll see that the probability of PB be greater than PA is actually 30% or 0.38. Or in this case, you can interpret that PA is actually better than PB. You believe that PA is on 62% of the time will be greater than PB. Yeah. So it's straightforward. It's not that after several iterations, after several repetitions, you'll see that most of the time in the confidence interval, blah 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 blah. No, 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 not something like that. It's straightforward. 62% of the time, PA will be greater than PB. That's it. Yeah, so it's straightforward. The interpretation. You'll get those nice plots with just these two lines. So the first one is for the trace plots, which I showed you earlier, and then the second one is for the posterior plot, the later one. Yeah. So another example. If you're not convinced yet, I'll give you this, the property ranking. So this is based on a real case I've faced before during my tenure at a startup company in Indonesia. So let's say we have some data like the following. So property A have 4 review scores, or yeah, stars basically. So the stars can be from 1 to 5. It's in a way similar to the picking a coffee shop problem we faced earlier. Yeah, we saw earlier. Property B has more review scores. It's around 20, if I recall correctly, and property C has 2 review scores. Both of them are 5s, but the problem is we only have two reviews so far. So which one is better from these three? Yeah. So we'll define the data something like this, and then if we choose to sort it using the frequencies way, we will sort them by the mean. This is a straightforward idea which would come to your mind first. But the problem is it is oblivious to n. As I mentioned earlier, you'll more likely to sort them like this. So C and then A then B. But the problem is you'll only have two n. So this does not reflect our uncertainty in the data. Maybe property C will have more fours or more threes in the future, and we don't know that yet. So with only two reviews, it is more likely to be so that the average will more likely to be lower in the future. So in the Bayesian sense, the recipe is something like this. You need to normalize your review scores so you can model it using the beta distribution. So this actually something similar to what we've seen before with the coin flip example or the A/B testing case. So it's something like this. But if this doesn't, if this is hard for you to understand, you can always go back to the probabilistic programming case where you model the score using a uniform distribution from 0 to 1. So basically, 0 is the worst and 1 is the best in this case, and you'll model the true value of the review score or the average value of the review score as yi, and then sorry, the score, and then yi is the observed value, right? So you'll get something like a binomial distribution with 5 as the n. So from 5 stars, what star would you get for each review? And you want to know the true value of this score, the average score, given that you'll see some of the observed review scores from your users. So in this case, the true score is the prior. You don't know anything yet, and then after you see more data, you see the posterior. Notice that the yi is in bold, so those it represents a vector of review scores. So several observed review scores in this case. Yeah. And the code will be something like this, quite straightforward as well, similar to the mathematical formulation we saw before. So the PM uniform score from 0 to 1, and then binomial n equals 5, and equals the score, which will be sampled after seeing the data. So it's something like this, and we define this as a function, so we can call this for each property, and we'll get something like this. And in this case, we can see that we are more certain about the true score of property B, since we have more review scores. Recall that property B has 20 reviews, uh, while property A only has 4 reviews, and property C has 2 reviews. So in this case, we are more certain about the property B. So the distribution is more tight in this case. Yeah, it's tighter in this case. Now the standings are C, then B, then A. But can we do better? I think most of you want to see that you are you believe more in property B, since it's has a decent score, a decent average score of 4.5, but you see more reviews there. So what can you do? If we want to be more conservative, instead of using the median, which is drawn by the dashed lines here, you can use the fifth percentile of the distribution. So by doing this, we'll see that property B is more likely to be the best in this case, compared to property C and property A. Sorry. Yeah. So but we can do something better. Instead of seeing something like this, it's kind of cluttered up. You can do something like this, to use the forest plot, basically with the rfis package, which is a complementary package of the PyMC3 library. for model diagnostics, and you'll see something like this, something simpler. And in this case, you see the leftmost points of each line here represent the um, if I recall correctly, the 3% or third percentile in this case. So you will sort them using the leftmost point of the lines. So property B, then property C, then property A. It's easy to see then. Yeah, the ranks change in this case. You are not um, sorting the properties based on the average score, but you are using the fifth percentile of the possible scores. So it's something like that. The problem is something sampling sometimes can be slow. So what you would do for bigger data is you would use some approximation like this. So you're approximating by normal distribution using the mean of uh, beta and the standard deviation of beta, and you'll get the fifth percentile using the mean minus 1.65 times the standard deviation of the beta distribution. So this would make it more scalable in this case. But most of the problems in Bayesian statistics don't have intractable integrals, so you don't really you can't really compute the normalizing constants. That's why we use sampling methods. And other examples, aside from what I've shown, we can find other examples. Something like this: Bayesian optimal pricing, with with 5 data points, pricing points. You'll see how people change their mind about the product, how many people would buy, things like that. And you'll get more than one line. So yeah, several lines that will represent the possible values of the quantity given the price, and you can maximize the profit by using that model. Yeah, so something like this. Another interesting case is the RT for COVID-19. So this is the effective reproduction number of COVID-19. You can see it on the URL down there. This is also using a Bayesian model, and you'll see some notebooks related to how to produce this model, basically. And 3 weeks ago, actually, we've just had the first PyMC conference, where I was also one of the speakers. You can see some of the talks there. You can find some inspirations. Maybe you'll find some interesting cases there as well. So go check the website. You'll see some of the videos there. You'll see the discussions there. So yeah, hopefully you'll learn something more from the talks. Actually, for probabilistic programming in Python, you can use other libraries aside from PyMC3. You can use Edward, the black cubes there, or Pyro, which is based on PyTorch, or TensorFlow probability as well. So it's a different breed of TensorFlow, the TensorFlow probability. PyMC4 is actually designed with TensorFlow probability, but they chose the PyMC developers chose to ditch the TensorFlow probability and instead opt with Theano with Jack's backend. So yeah, it's an interesting thing to see Theano be revived again. Uh, yeah, so if you don't know what to choose, you can see this article, a tour of probabilistic programming language APIs by Con Carroll. You'll see the comparison of those 4 libraries and other libraries as well, like PyStan, or yeah, I guess there's also Stan as well. So yeah, so you'll see something like that. But for me personally, I really like the API design of PyMC3, and it's quite fast as well. So the key takeaways from this talk are the first one: Bayesian inference can be made easy with probabilistic programming. You see that with some basic probability understanding, you can model the problem, and you leave the rest to PyMC3. And I did not cover Bayesian statistics in details in this talk. It would be much longer if I had uh, covered it. But you can start with basic probability theory. Like I mentioned, you'll see you should see courses like Harvard Stat 110 or CS 109 from Stanford. Those two great courses cover a lot of basic probability theory, and um, despite not being able to understand or most of the sampling methods like the nuts or Markov chain Monte Carlo or Hamiltonian Monte Carlo or things like that, you can actually use Bayesian inference by using probabilistic programming and help you to understand small data. Yeah, where by nature it's hard to obtain more data. So to conclude, Don Berry said that Bayesian inference is hard in the sense that thinking is hard. So yeah, that should end this talk. And these are some of the references. You could look them up online. Thank you for listening and thank you for the indulgence.
Okay, thank you so much, Mr. Ali Akbar. It's such an amazing talk that you have shared to us. It certainly opens a new perspective for us. And unfortunately, we ran out of time. Thank you so much, Mr.
Yep.
Ali Akbar, for the
Once again.
time.
Yep.
Thank you so much. And also for all of you who participate in the session, I'll see you soon in another session. And allow me to close this session. See you soon in another session. Bye bye.
Yep.
Thank you, Mr.
Bye.
Ali.
Thanks. Yep. Thank you.